two blocks A and B of masses 3m and m are respectively connected by a massless and inextensible string. The whole system is suspended by a massless spring as shown in, okay, so massless and inextensible string and massless spring. The magnitudes of acceleration of A and B immediately after, this phrase is really important here, immediately after the string is cut out. See, I don't have the diagram here, so those who have the handout, I think the diagram is labeled there. So give me a minute, I'll draw the necessary diagrams, then we'll go on to the solution. So now we have the initial condition. Okay, so what we'll do is we'll try to divide this question into the solution into three parts. One, before the cutting of the spring. Second, immediately after the cutting of the string. And the third one, what we'll do is we'll try to understand the comparison between impulsive and non-impulsive forces. So you may be wondering, why am I talking about that? As a third part, that will become more clear to you once we discuss the second part. So first part is before cutting the string. And what do we have here? The system is at rest, which means sigma fx and sigma fy will both be equal to 0, right? By Newton's second law of motion. Okay, now let us see the various forces acting along here. So we have the wall, the blocks, wall and the block. Immediately between them there is spring. A and B is connected via a string. I repeat, wall and A are connected by a spring. A and B are connected by a string, right? Right. Now let's see what happens here as a result of drawing the free body diagram of A. So what are the various forces acting on A? See, we know that if the net elongation is downwards, the restoring force or the spring force would be F is equal to Kx acting upwards. Okay, right. So that's it. Next up, we have weight of the body which is acting downwards, right? So that would be 3m into g. And since there is a point of contact between A and B, repeat, since there is a point of contact between A and B, this string will be pulled towards B, and therefore tension would act away from this point of contact. We'll draw it one more time. So for the body A, there is spring force acting opposite direction, Kx. We have weight of the body acting downwards, which is 3m into g, right? And then what we also have is tension along the string along the string connecting A and B away from the point of contact. This is the point of contact. Away from the point of contact is acting tension. Now, if we apply sigma Fy is equal to 0 here, what do we get? What we get is T plus 3mg is equal to Kx. Now, what is sigma Fy? It simply means that sum of the forces acting in the vertical direction are equal, which means sum of the forces acting downwards will be equal to sum of the forces acting upwards. Now, since it is acting downwards, I have taken this as positive, and this is going upwards, I am taking Kx as negative. It transposes and becomes Kx. Okay, so that's there. Now let us see what happens with the string alone. So again, see, in the original picture, what is present here? The body A is present here, which means this body B will experience a tension away from the point of contact. This is the point of contact, and it will experience force away from the point of contact, and it will also have a weight acting downwards. So if you apply sigma Fy is equal to 0 here, what do you get? What you get is mg is equal to T, right? So this is important. It simply means that tension acting in the string is actually equal to the weight of the mass it is connected to it. Why is it important? Let's see. It is important because now, instead of this tension, what can you write here? You can bring this relationship here. And instead of tension, you can write here mg. So now mg plus 3mg is equal to Kx, and therefore 4mg is equal to Kx, which means the spring constant here can otherwise be written as 4mg. So we have a spring with a spring constant 4 mg into x. Oh, sorry, x is equal, k is equal to 4 mg. Right. Now let us see the case of after cutting the string. Okay. Now, one key word to understand this question is really important, which is cutting of the string immediately after. So we have immediately after cutting. That word is really important. Why is it important? That comes in part 3. So this is immediately after. Say for example, you were observing a t is equal to 1 second and then you are cutting a t is equal to 1.002 seconds. That is immediately after cutting. Okay, you're not observing this scenario after t is equal to 4 seconds. No, there's a difference. Okay, now what is the condition here? And the block A, the string is between A and B. When the string is cut, what happens is the primary effect. See, there is some tension between the points A and B. And when the string is cut, what happens with the tension? What happens with the tension is the tension becomes 0. Now, when the string is cut, the string is hanging without any tension. Or in other words, we can say that the tension is equal to 0. Right? The tension is equal to 0. Now, okay, give me a second. Yeah, the tension is equal to 0. Similarly, for the body B, if you try to visualize this, this was the tension, the string here. The string would be now almost vertical, but without any tension. B here, the string was like this. There was some tension, but it will now fall down. And for B also, string is hanging without any tension, which means tension is 0 in the string for B as well, right? Now let us see. Excuse me. Now let us see how to solve the how to write the free body diagram. So free body diagram and how to apply Newton's second law of motion. So if we draw the free body diagram here for A, we know that spring is now under the restoration effect. Why? Because the string is cut. It was elongating. Now, well, if I have to draw this diagram correctly, the length of the spring should actually come down. Why should it come down? Because, give me a second. Yeah, so this is how it should look like, right? Because the spring is now moving upwards. Okay. Now, since it is moving upwards, therefore the spring force will be acting kx. So yes, we have spring force acting kx. What other forces are acting? See, since it is a weight, definitely being a weight, which force will act? Weight will act. So we have not mg, it will have be 3m into g, right? 3m into g. If you want, you can write down tension also for your clarity if you want it. Well, which is actually 0. Now, since the net direction of motion is towards the upward direction, all forces along the upward direction will be given as positive. Since kx is along the direction of motion, we will give kx as positive, and this will 3 mg as negative. So if we were to write sigma fy is equal to, is it 0? No, there is some acceleration, so that will be m into a. What is sigma fy? Plus kx. Y plus kx, positive along the direction of motion. So we have plus, my bad, we have plus kx minus 3m into g. Oh wait, this is not ma, this is 3m into a. Will be equal to 3m into a, right? Okay. Now, what is kx from the previous derivation? Kx is actually equal to 4 mg. We derived in the first part. Now, we can write that 4 mg minus 3 mg is equal to 3 ma, and therefore, mg is equal to 3 ma. M and m will cancel. So, what we get is a is equal to g by 3. Therefore, this body A will move up with a velocity with an acceleration of g by 3. Now, let us see the case of B also. See, so what happens for B is, if you draw the free body diagram of P, earlier what was acting there? Tension was acting. That tension is now 0. So the only force acting on B is m into g. So if we were to write sigma fy is equal to m into a, what is sigma fy? Since B will come downwards, mg will be taken as positive. minus t is equal to ma. The value of t is 0. So what you get is mg is equal to ma. And therefore what you get is m and m will cancel. What you get is g is a, which means this body is under free fall. Right? So the body is under free fall. Okay. Free fall. So we found the value of a for the body A and for body B, which means let us go back to the answer now. Yeah, so the acceleration of A is g by 3 and acceleration of B is g, which means the correct option is okay, A is g by 3. Okay, there might be some problem with this. Okay, this is the correct option, g by 3 and g, right? Now let us see one more thing, which is a very important point when it comes to the discussion on impulsive and non-impulsive forces. You might be wondering why did I take that value as 0? So we'll just go through a very small explanation here. See, this is a wall which has a hanging portion like this. I have a spring here. Now, if I attach a mass here, right? If I attach a mass here, this mass will definitely extend the spring, right? This mass will definitely extend the spring. And when this mass will extend the spring, there will be some restoring force acting upon the spring, which is what we call as F is equal to kx. Now, there was a string here. The moment you cut the spring, this restoring force will come into picture and it will completely try to decompress the spring, and eventually it will come like this. But if this is at t is equal to 0, this is at t is equal to 1 second, and if you are cutting this at t is equal to 1.00, okay, let us say if you cut that at t is equal to 2 seconds, right? Now at t is equal to 2.00 seconds, or maybe say t is equal to 2.2 seconds, what happens is the spring won't come to its natural length originally. So see, this is the natural length, right? This is the natural length of the spring. It won't come to the natural length originally, the original natural length very instantly. It will take some time. Maybe at t is equal to 4 seconds, the spring is back to the natural length. So since it takes some time for the spring to come back to the normal position, we call these kind of forces as these kind of forces as non-impulsive forces. Whereas when you discuss impulsive forces, say for example, this is the wall here. We have a block attached to a string which is hanging on the wall. If you cut the string, immediately what happens is, see, this block will definitely fall down, right? This block will fall down. And what will happen to the string? There was some tension acting in the string which is caused due to this mass, and that mass is not present now, which means the tension acting here will be equal to 0 instantly, and therefore tension is an impulsive force in this example. But what you should understand is tension can be both impulsive and non-impulsive as well. Something that we'll discuss much, not here. I wouldn't say that's really essential for the NEET aspirants. Maybe for the JEE means. But of course, if you have to understand the concept, please make sure you go through the theory given. Right. So that's it for this set of questions. Moving on to the next question.